Sequential circuits rely on timing, and timing can be a really tricky issue. We'll look at some of the different timing issues and pitfalls that can happen with sequential circuits. To determine how small we can make the clock period, we need to determine the longest delay from the triggering edge of the clock to the next triggering edge. These delays are measured on all such paths in the circuits down which the changing signals propagate. For both types, edge and pulse triggered, there is a minimum time called the setup time. During setup time, S and R or D inputs must be maintained at a constant value prior to the occurrence of the clock transition that causes the output to change. Another item to consider is the hold time. This is a minimum time for which the S and R or the D inputs must not change after the application of a clock transition that causes the output to change. In addition, there is a minimum clock pulse width to ensure the sample has enough time to capture the input values correctly. Among these parameters, the ones that differ most between pulse-triggered and edge-triggered flip-flops is the setup time. The propagation delay times of the flip-flops are defined as the interval between the triggering clock edge and the stabilization of the output to a new value. Since the changes of the flip-flop outputs are to be separated from the control by the flip-flop inputs, the minimum propagation delay time should be no longer than the hold time for correct operation. You can find these parameters in the manufacturer's data books for specific integrated circuit products. There are two ways to analyze performance timing for sequential circuits: maximum input to output delay and the maximum clock frequency. To determine how small we can make the clock period, we need to determine the longest delay from the triggering edge of the clock to the next triggering edge of the clock. We measured these delays on all paths in the circuit where the changing signals propagate. In particular, each of these fast delays has three components: a flip-flop propagation delay known as TPD-FF, a combinational logic delay through the chain of gates along the path is known as TPD-COM, and a flip-flop setup time known as TS. As the signal change propagates down the path, it's delayed successively by an amount equal to each of these delays. Let's look at an example. Suppose that all flip-flops used are the same and have a propagation delay of 0.2 nanoseconds, and a setup time of 0.1 nanoseconds. Then the longest path beginning and ending with the flip-flop will be the path with largest combination delay. Suppose that's 1.3 nanoseconds. If the minimum allowable clock period, TP, has been set to 1.5 nanoseconds, then we have the following equation. When we solve this equation, we end up with the slack equal to minus 0.1 seconds. Now, we're assuming sub-light speed physics here, so the minimum allowable clock period of 1.5 is too small, and TP should be equal to at least 1.6 nanoseconds. We can calculate the maximum frequency as 1 divided by 1.6 nanoseconds, which is equal to 625 megahertz. Note that the hold time for a flip-flop, TH, does not appear in this clock period equation. An asynchronous circuit has one or more state variable changes that occur without being directly synchronized by the special clock input. Instead, an asynchronous circuit may change state in response to any of its inputs. The interactions between synchronous and asynchronous circuits can be strange to say the least. Interactions between two synchronous circuits having clocks that are unrelated to each other also get a bit weird. Now, philosophically, we can model every flip-flop or latch as an asynchronous circuit if the clock is regarded as just another input rather than a special clock input for synchronization. However, the book recommends avoiding asynchronous design since it's very difficult to ensure the correct operation. Here we consider three different types of synchronous-asynchronous interactions as depicted in this figure. The problems of driving an asynchronous circuit with the outputs of a synchronous circuit are primarily due to combinational circuit hazards. The problem of an asynchronous circuit driving a synchronous circuit is different. Here we have contact bounce, generated by manually operated push buttons or switches. Signals originating from a push button don't get synchronized with an internal electronic clock, and they can occur at any time. We have the same problem when we have two different clocks. The circuit in Figure 440 can illustrate erroneous behavior due to an input signal not being synchronized with the clock. The circuit is initialized by using a reset signal which sets the state of the circuit to S0. As long as ready is equal to 1, the circuit cycles through the states S0, S1, and S2. If ready is equal to 0, we wait in state S0 until ready is equal to 1, which causes it to go to state 1. Also, the state can change from S1 to S2 and S2 to S0 with ready equal to 0. All combinations of state variables are invalid during the normal operation of the circuit. If ready is asynchronous with respect to the clock, it means that it can change any time during the clock period, and we run into some subtle timing problems such as the one shown in Figure B, which results in a locked circuit, and Figure C, which ends up in an invalid state. We can fix this circuit by adding a synchronizing D flip-flop and ensuring the minimum interval specification is met by the asynchronous input. Latches are used to construct flip-flops, and they have three potential states: stable 1, stable 0, and metastable. When an input to a cross-coupled pair of latch gates changes just the right timing relationship with the clock edge, a narrow pulse can be generated. The pulse may just have enough energy to change the latch state to a metastable point, where both gates have equal output values with voltages between 1 and 0. Like the mechanical system, the latch and hence the flip-flop containing will eventually go to 0 or 1. However, the length of time it remains in the metastable state is non-deterministic. It's fairly unlikely, but this can happen. If it happens for an entire clock period, then things can go very bad. The authors discuss an experiment where this happened at Washington University in St. Louis. We can never eliminate this problem totally, but having a series of synchronizing flip-flops helps to reduce its probability. Just because there's a clock does not mean the circuit is synchronous. For example, in a ripple counter, the clock drives most one flip-flop clock input directly. All other clock inputs driving the flip-flops are actually state variables, so the changes in state variables that are outputs of these flip-flops are not synchronous with the clock. For a 16-bit ripple carry counter, the worst-case scenario is where all flip-flops change state, and the most significant bit changes 16 flip-flop delays after the clock edge of the first flip-flop. Another problem can occur with something known as a suicide counter. Due to the attached NAND gate and its connections, when the count becomes 0, 1, 1, 0, or 6 in response to a positive edge, the NAND produces 0, causing the 4 flip-flops to be cleared, giving A0. Now, if flip-flop A1 is slow enough and A2 fast enough, the state 0010 could result instead of 0000. Now, there are certainly situations where you must use asynchronous circuits to get the desired behavior for a system, but these situations are far fewer than the cases where someone thinks they need an asynchronous circuit, or a synchronous circuit that's really asynchronous. So try to avoid asynchronous design whenever you can. That's a wrap for Module 4. Thanks so much as always for watching, and be sure to check La Lima for assignments.